Alright, we're going to get started with Lecture 5, Electron Configurations. And here in Lecture 5, what we're going to do is we're going to pick up where we left off with atomic orbitals and go further with that, as well as talk about this new idea of electron configurations. So our essential questions for this lecture are going to be: how are electrons arranged in subshells or in orbitals, and how do we predict the electron configurations for an atom? So make sure you're able to answer those two questions by the time we're done here with this lecture. Now, before we go on, I want to point out to you this idea of subshells and orbitals. Again, subshells is just another name for an orbital. All right, and remember that we talked about orbital shapes last time, and if you recall, there are s orbitals, there are p orbitals, d orbitals, f orbitals, and so forth. In this class, all you need to worry about mainly is s, p, and d, and sometimes f orbitals. All right. And recall that an orbital, all it is a probability of where an electron would occur, the probability of finding an electron within a specific space in the atom itself. All right? And we're going to talk a little bit about what that really means within relation to electron energy shells in this particular lecture. Alright, so let's go on here and let's take this opportunity to review the shapes of these atomic orbitals or subshells. You got a p or s orbital. Recall that an s orbital is very spherical in nature. S orbital. There are only one type of s orbital that exists in atoms. And then you have a p orbital. And the p orbital kind of are lobes or look like dumbbells here. And again, you got all these probability points inside there where an electron can occur anywhere in those. And so, if you remember, there are three types. This would be a px because it's along the x-axis. You have, this is a y. What am I thinking? Py. And then you have a px that's along the x-axis here. All the probability points. There's going to be a lot more probability points than what I can put in. Px. And then you'll have another one, the pz, and that's going to be poking out at the screen at you and poking you in the eye, really. So that's pz. So forth. Again, probability where an electron will occur. Okay, and so there are three different types of p orbitals that are just spatially arranged differently. All right, they look the same though. And then we had d orbitals. And I'm not expecting you to be able to draw the d orbitals. I gave you a diagram of the structure of d orbitals in the last lecture, and so you can go back and refer to that. And you have a nice one in your textbook as well, looking at what p orbitals look like in their shapes. But I do need you to know that there are 5 d orbitals. So there's one type of s, there are 3 types of p, and there are 5 types of d orbitals. And while we're at this, we might as well also include that there are 7 types of f orbitals. And those f orbitals have very strange geometrical shapes to them, so we're going to kind of ignore them a little bit, okay, and not worry about what their shapes are. So just remember, 1 type of s, 3 types of p's, 5 types of d's, and 7 f orbitals. All right? Now, let's put this in perspective using the Bohr model a little bit and combine atomic orbitals and energy shells together and take a look. Okay, so let's say this, the first energy level, which is n equals 1, okay? It contains what is known as 1s orbital, okay? Now the 1s, the 1 in front of it, just signifies that we have an s orbital in the first shell, okay? And we're going to represent this by just using a simple line like this, okay? So every time we talk about an orbital, we're going to use just a dashed line, and we're going to put the orbital name underneath there, and so this is going to be our 1s, okay? And so we only have one orbital in the first energy shell. In the second shell, which again is n equals 2, that contains a 2s orbital. Now, the 2s, again, the 2 just represents that we have an s orbital in the second energy shell. So that's what this 2 represents, is an s orbital in the second energy shell. And we're also going to have 3 p orbitals in the second shell. And so we're going to dignify those by writing 3 dashed lines to represent the 3 different types of p orbitals. And again, the 2 represents that we have a p orbital in the second energy shell. And so we can call this the px, py, and the pz. And it doesn't really matter what order the x, y, and z orbitals are in. You can reverse them any way you want, but we'll just do it this way, x, y, and z. Alright? Now, also notice that I have the p orbitals just slightly above the s orbital here. And that is because the p orbitals have more energy than the s orbitals. So even though s orbitals and p orbitals exist in the second energy shell, they have different amounts of energy. So if an electron is in a p orbital, it's going to have more energy than if it was in the s orbital. And that will become important later on as we look at this. Okay? So are we pretty good with this notation so far? Let's move on and let's talk about some specific vocabulary here as we put this all together. All right. The Aufbau principle. You need to know the Aufbau principle and what it means. Sometimes we call it the building up principle. And what the Aufbau principle just states is that electrons are always placed in orbitals with the lowest energy first. So let me kind of explain how this works. Let's come back and draw our 1s orbital, and that's for the first energy level, and then our 2s orbital, and then our p's, 2 p's, okay, x, y, and z, okay? Now, if you remember, in the Bohr model, energy increases as you move away from the nucleus. So, I'm going to place electrons, according to the Aufbau principle, in the lowest energy subshell that I can do that, okay? And so, since the first energy level has the lowest energy, my first electron has to be put in the 1s orbital. Okay, so this is where I'm going to put my first electron for an atom. Now, how do we represent electrons when we use these orbital diagrams, which is what we're doing? And that is we use arrows. Okay, so I'm going to place an arrow here, and an up arrow represents one electron in that energy shell. Okay. Now, at this point, we're going to also include what is called the Pauli exclusion principle. And that's here at question number 2. And it says, what is the Pauli exclusion principle? Since we're on this topic, we might as well do that. The Pauli exclusion principle says that no more than 2 electrons can occupy any one orbital. So in the first orbital, the 1s orbital, we can only have a maximum of 2 electrons in there. And the Pauli exclusion principle also states that if 2 electrons are in the same orbital, they must have opposite directions, or what we often call as opposite spins. All right, so actually fill that in, opposite spins or opposite directions. So spin. All right. Now, to represent that electrons have opposite spins, we use up and down arrows. So if I have 2 electrons in the 1s orbital, then I'm going to place a down arrow to represent the 2 electrons with opposite spins. One up, one down. All right. Now, the next electron, if I had a third electron, is going to go in the next lowest energy shell according to the Aufbau principle. And so that would have to be the 2s. The 2s is lower in energy than the 2p. So my next electron would go here. All right. And then if I had a fourth electron, it would still go in the 2s, but again, it would have a down arrow representing an electron with an opposite spin, like so. And then where would you expect me to put the fifth electron? That's right, it would be in one of the p orbitals. Now, it doesn't matter which p orbital I place the next electron, because all p orbitals have the same exact amount of energy. So whether it's the px, the py, or the pz, same energy, just different spatial orientation. So I'm just going to go ahead and put an electron here in that p orbital. All right? And so what I've done is I've created or followed 2 rules, 2 principles, the Aufbau principle and the Pauli exclusion principle. Again, the Aufbau principle is I put electrons in the lowest energy orbitals first, fill them up, and then move to the next one, and so forth. And also with the Pauli exclusion principle, I can only have 2 electrons in an orbital, and they must have opposite spins or directions, right? Alright, so how do you draw orbital diagrams? Well, we've kind of already begun that process of drawing an orbital diagram. But let's start with specific elements, okay, and start drawing specific element diagrams, orbital diagrams, using the Aufbau principle and the Pauli exclusion principle. Now, it might help you to have a periodic table, so you might want to pause this and get out a periodic table so you can take a look at it as we go through and do this. Alright, now that you got a periodic table in front of you, if you look at the periodic table, you will notice that the first element on the periodic table is hydrogen. Hydrogen has 1 electron. Well, where is that 1 electron for hydrogen going to be? Well, if you remember, we have in the first energy shell, n equals 1, we have a 1s orbital, right? So we are going to fill, and actually let's go ahead and put some of these other ones. So the second energy level, you have what, a 2s, and then you have slightly higher in energy, the 2p's, right? And then let's show a third energy level. And in the third energy level, you're going to have a 3s, and you're going to have our 3p's. And we're just going to leave it at that for the time being, okay? So this is what an orbital diagram is going to look like. Now for hydrogen then, you have 1 electron. Where are you going to put that 1 electron? Well, obviously, according to the Aufbau principle, you have to put it in the lowest energy level, which is going to be the 1s. So that's what I'm going to do. All right. So this is would represent more or less hydrogen. So the next element on the periodic table is helium. Now helium has 2 electrons. So it's going to have 1 electron in the 1s, and you're going to add the second electron to, that's right, the 1s. But it's going to have a down arrow because the Pauli exclusion principle says that we can only have 2 electrons in an orbital, and they must have opposite spins or directions. Okay? Now, going to lithium. Lithium starts a new period, which identifies by our shell, the second shell. And so we are going to put an electron for lithium in the lowest orbital, which would be the 2s, like so. And what's after lithium? Well, beryllium. So beryllium would have an electron in the 2s, like so. Alright? Now, after beryllium, you're going to jump over to boron. And so where are we going to put the next electron? Well, it's going to be in the p orbital. So this would be boron's orbital diagram. Alright? And after boron comes carbon. So we have a decision to make. Where do we put the next electron? Do we put it in the same p orbital as we did for boron, or do we put it into a different p orbital? Well, it turns out that we're going to actually put it in a different p orbital with the same spin. Okay, now this is known as Hund's rule. Okay, so Hund's rule states this. Hund's rule says if more than one orbital in a sublevel is available, electrons occupy different orbitals with parallel spins. All right. So again, since I have 3p sublevels, so let's. If I have 3p sublevels, let's get this back. Oops. Okay, if I have 3p sublevels, so 1, 2, 3. So let's do our 2p's here and our 2s. And we already have electrons here in our 2s and then 1 in our p. Okay? So essentially, the next electron that goes into the 2p for carbon, according to Hund's rule, because all these p subshells have the same energy, we're going to put the next one here. And that would be for carbon. And then what comes after carbon is nitrogen, and so we'd fill this one with nitrogen. Now, once we have at least one electron in each one of those p orbitals, then we're going to come back to our first p orbital, and we're going to fill in an electron with an opposite spin. And we're going to keep on doing that until we fill up all of those p orbitals, okay, to follow Hund's rule. Okay, so let's go back and let's see if we can make an orbital diagram for the element oxygen. Okay, so let's write oxygen. Oops. Let's write oxygen up here. All right. Now, so let's do our orbital diagram. N equals 1, and that's going to be a 1s. N equals 2, it's going to be a 2s. And we have our 2p's. And then we have 3, and that's going to be our 3s. And then we have our 3p's. Alright? So oxygen. So oxygen has how many electrons? It has 8 electrons, right? So we need to fill up the orbital diagram with 8 electrons. And we have to follow Hund's rule, the Pauli exclusion principle, and the Aufbau principle. So with the Aufbau principle, we're going to fill up, start out with the lowest energy subshell and put electrons in there. And so we're going to do that. There's 1 electron. Remember, we need 8 electrons total. So there's 1 electron. And then we're going to fill it, put another electron with an opposite spin to apply to the Pauli exclusion principle. And then we're going to go to the second level. We're going to do the 2s because it's lower in energy than the 2p. Do that. So we've used up 4. And then we're going to go to our p. And now that's 5 electrons. So we have 3 more electrons. Right? So where are we going to put those 3 more electrons? Well, we have to follow Hund's rule. And so since we have 3 different p orbitals here, we're going to have to put 1 electron in each one, obeying Hund's rule. So there's 2 more. And now, notice that those all have the same spin. They're all up arrows. And then the last electron is going to go back into our first 2p orbital with opposite spin. And so this is the orbital diagram for oxygen right there. All right? Not too bad. Let's try another element. Let's try one that's, let's try phosphorus. Okay, we'll do phosphorus. P. Phosphorus. Phosphorus, if you look at your periodic table, should have or need 15 electrons. Okay, so again, we erase these electrons here. And then let's see if we can fill this up together. Okay, so I'm going to fill 1 there and 1 there. Those are 2 out of the 15. 1 there and 1 there. 3. And then we're going to follow Hund's rule, and we're going to fill up here, here, here. And then come back and fill that one up. Fill this one up, and fill that one back up. So now we've used a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons. Okay, so we have 5 more to go. So again, following the Aufbau principle, we're now going to go to the 3rd energy level, which is on the 3rd period, because you'll notice that phosphorus is on period 3. So we have to go to the 3rd energy level. And we're going to put an electron with an up arrow, and then one with a down arrow, and the 3s. And so the 3s is now filled. So now we got to go to the 3p. And now we have 3 more electrons to go. So we're going to put 1 in the p with an up arrow. And we're going to follow Hund's rule, and we'll put another one there because of Hund's rule, and the last one in the other p orbital, all with the same up arrows or the same spin direction. And that would be the orbital diagram for phosphorus. Right? How are we doing so far? Hopefully doing pretty good. Okay, so we're going to erase this now. And let's try another one. Let's see if we can get into the D's a little bit, okay? Now, one thing you need to understand about D's, things get a little bit complicated. So the D's, you would think in the 3rd shell we might have d orbitals, which we do. The only thing is that the 4s is slightly lower in energy than the 3ds. Right? So we're actually going to have 2, 3, the 4p's here, and the 3ds, 1, 2, 3, 4, 5, remember there's 5 of them, are actually going to be higher in energy than the 4s. Now that may sound strange to you, but that's the way it is. The 3ds, those d orbitals that are in the 3rd energy shell, are higher in energy than the 4s. Okay, so there's kind of an overlap there. So let us say that we're going to do chromium. No, let's don't, do chromium. Let's do manganese. Manganese, which is Mn, has a total of 25 electrons. So we got to fill in 25 electrons. So we're going to follow all the principles that we know. So we're going to put in 2 electrons in the 1s. We're going to put 2 electrons in the 2s. And then we're going to fill up electrons using Hund's rules and the p like so, and then go back. And then we're going to go to the 3s. Then we're going to go to 3p, follow Hund's rule, and then go back. Now, at this point, instead of putting electrons in the 3d, we're actually going to put electrons in the 4s first. And we're going to fill up the 4s with electrons. Now that's going to leave us with 1, 2, 3, 4, 5 more electrons. And those 5 electrons are going to now go in the 3Ds. And they're going to follow Hund's rule just like we did with the p orbitals. We're going to fill in 1 electron in each one of those p orbitals first, or d orbitals first. Alright? Before we go back and fill them in. So this would be the orbital diagram for manganese. Alright? Now let's kind of continue where we're at. Instead of erasing all of this, we'll just kind of go to another element. Let's say we're going to do arsenic, As. And arsenic has 33. So arsenic, you're going to continue where you're at, and you're going to fill in all of the d orbitals. Oops. Just lost it. Alright. So I just lost my whole picture. It's all erased. That's alright. Let me see if I can rewrite this. Okay, so alright, so we have n equals 1. So we have the 1s. N equals 2. We have the 2s. And then we have 2 p's. And then we have n equals 3. We have the 3s. And then we have the 3 p's. And then we have the 4th energy shell, which gives us the 4s. And then we have the 4 p's. But the 3d's are kind of in between. In between, so 1, 2, 3, 4, 5. That would be the 3d's. So with arsenic, As, we have again 33 electrons. So we're going to fill in 2 electrons there, opposite spins, 2 there. Essentially going to fill all these up. Go to the 3s, Hund's rule, 3 p's, then go back. And we do the 4s because it's lower in energy than the 3d's. Then we're going to do the 3d's. We're going to follow Hund's rule, 1 in each one. Then we come back, fill those in. Okay, now at this point, that leaves us with 3 more electrons. And those last 3 electrons are going to go in the 4p orbital, like so. Just like that. And that would be the orbital diagram for arsenic. Alright? So we'll relook at this if you need to on these orbital diagrams. We'll practice some more in class and so forth. Okay, so we're going to move on. Alright, now the periodic table, and actually we're getting to the point where I probably need to stop and do a part 2 on this video. So this is what we're going to do. This is going to be considered part 1, and we're going to stop the video here, and then we're going to pick this up on part 2, the rest of this lecture.